300 kilometers north of Yellowknife, the landscape looks like absolute nothingness. Low gray granite outcrops, scattered dwarf birch, wind-scoured eskers, and thousands of shallow, unnamed lakes stretching to the Arctic horizon. From a twin-engine plane overhead, there are no roads, no tree lines, and no visible signs of human history. For decades, geological maps marked this portion of the Northwest Territories as a sterile shield of ancient rock. Beneath this frozen crust lies the richest concentration of diamond-bearing kimberlite pipes ever uncovered in North America. What is remarkable is not that the diamonds were buried 300 meters deep, but that major mining conglomerates and state survey teams walked directly over the indicators for nearly a century without recognizing what was sitting in the till. How did two independent geologists track microscopic mineral grains across thousands of kilometers of ice-scoured tundra to prove the global mining establishment entirely wrong? For most of the 20th century, the accepted scientific consensus among economic geologists was that North America lacked diamondiferous kimberlite pipes. Diamonds require extreme pressure and temperatures above 1100 degrees Celsius, conditions found only in the mantle roots beneath ancient stable continental crusts known as cratons. The Slave Craton, a massive slab of Archean rock spanning over 200,000 square kilometers between Great Slave Lake and the Arctic Ocean, certainly fit the age requirement, being over 2.5 billion years old. However, early reconnaissance surveys by the Geological Survey of Canada in the 1950s focused almost exclusively on surface gold and base metals, leaving the vast interior tundra unexamined for kimberlites. Mining majors like De Beers examined southern regions and largely dismissed the Canadian Shield, assuming glacial erosion during the Pleistocene epoch had scraped away any pipe structures that might have once existed. That assumption was entirely reasonable at the time, given that glaciers up to 3 kilometers thick had repeatedly swept across the continent, grinding the surface down to bedrock. The first crack in that belief appeared in the late 1970s. A geologist named Chuck Fipke, working alongside his partner Stuart Bluesen, began testing a different hypothesis. Fipke was not backed by a major mining corporation. He operated through a small exploration outfit called Met Minerals. Instead of looking for diamonds themselves, which are extraordinarily rare even in rich deposits, Fipke targeted indicator minerals, specifically G10 pyrope garnets, chrome diopside, and pyrrolmonite. These dense, heavy minerals are brought up from the mantle alongside diamonds inside kimberlite magma. When a glacier overrides a kimberlite pipe, it shears off the top of the structure and drags these indicator minerals downwind, creating a teardrop-shaped dispersal train through the glacial till that can stretch for hundreds of kilometers. Beginning in 1978, Fipke and Bluesen began taking soil samples across British Columbia, Alberta, and the Northwest Territories, painstakingly panning stream sediments and glacial eskers. Using an electron microprobe at the University of British Columbia, Fipke analyzed the chemical composition of individual garnet grains. He was specifically searching for subcalcic, high-chromium pyrope garnets, classified as G10 garnets, which form under the exact pressure and temperature window where diamonds remain stable in the mantle. By 1985, Fipke had picked up a distinct trail of G10 garnets in the Northwest Territories, but the trail was complex. The continental ice sheets had advanced and retreated in multiple directions over the last 2 million years, scrambling the mineral paths across the Slave Craton. Fipke and Bluesen spent 5 years tracing that chemical trail backwards against the historical direction of ice flow. They flew low-level magnetometry surveys in a float plane, looking for subtle magnetic depressions in the Precambrian granite where soft kimberlite rock had eroded faster than the surrounding shield, forming shallow lakes. In September 1991, drilling through the ice on a small body of water near Lac de Gras, their diamond-tipped drill bit brought up a core sample of dark, brecciated kimberlite rock from a structure named the Point Lake Pipe. Microscopic analysis of the first 45 kilograms of core yielded 81 small diamonds. On November 25, 1991, Met Minerals publicly announced the discovery. Within months, the quiet tundra around Lac de Gras became the focal point of the largest land staking rush in North American history, with exploration crews staking claims across more than 20 million hectares of the Northwest Territories. To understand why the diamonds were hidden so effectively, one has to go back 54 million years to the Eocene epoch. At that time, the mantle root beneath the Slave Craton experienced a sudden, violent release of gas-driven magma. Kimberlite is not a standard volcanic eruption that flows smoothly over the land. It is a supersonic blast of volatile fluid, packed with carbon dioxide and water vapor, punching straight through 50 kilometers of solid granite at speeds reaching 200 meters per second. As this supersonic slurry nears the surface, the expanding gas shatters the surrounding bedrock, blasting out a narrow, carrot-shaped pipe known as a diatreme. Inside this pipe, mantle rock, xenoliths, and microdiamonds cool rapidly, freezing the diamond crystals intact before high temperatures can convert them into worthless graphite. In the case of the Lac de Gras field, dozens of these volcanic pipes punch through the granitic basement rock in a relatively tight cluster. Over the subsequent tens of millions of years, tectonic uplift and weathering slowly eroded the upper volcanic cones. Then came the Laurentide ice sheet. During the Quaternary glaciation, ice up to 3,000 meters thick advanced across the Slave Craton, dragging debris along its base like giant sandpaper. Because kimberlite contains soft clay minerals like serpentine and phlogopite, the advancing glaciers carved deep depressions directly into the tops of the pipes, gouging out the soft kimberlite while leaving the surrounding granite intact. When the ice sheet finally retreated roughly 9,000 years ago, meltwater filled these gouged depressions, covering almost every diamond pipe in the Northwest Territories under 10 to 50 meters of water and soft lakebed sediment. This created a severe geological paradox. Early geologists mapping the region saw only thousands of identical-looking lakes. The bedrock outcrops visible between the lakes consisted of uniform Archean granite and metasedimentary rocks, offering zero hint of the mantle diatremes resting beneath the water. Furthermore, the Laurentide ice sheet did not move in a simple straight line. Geological Survey of Canada studies show that over successive glacial cycles, the ice flow direction over Lac de Gras shifted from southwest to northwest, and finally, toward the west-northwest. This shifting motion smeared the indicator mineral trains across hundreds of square kilometers, creating complex, overlapping fan patterns in the till rather than a single tidy line pointing back to an origin. A prospector looking for a simple linear trail of garnets would inevitably track them to a dead end in open water or lose the signal entirely in thick esker sands. Early sampling programs conducted by major mining firms in the 1960s and 70s frequently failed because they collected samples at arbitrary intervals of tens of kilometers, completely missing the narrow, high-concentration plumes of G10 garnets and chrome diopsides. Fipke and Blusen succeeded because they recognized that the ice had reshaped the surface drainage and altered the overburdened geography in ways that standard geological models of the era had not accounted for. By tracking heavy minerals through the quaternary till with millimeter-level precision, Fipke traced the mineral trail back to its point of disappearance at the shoreline of Lac de Gras. Yet locating the general lake area was only half the battle. How could anyone prove that a specific body of water hid a viable diamond pipe without spending millions of dollars drilling blind holes through dozens of frozen lakes? The breakthrough came not from a single dramatic discovery, but from the convergence of heavy mineral chemistry and airborne geophysical surveys. By the late 1980s, Fipke was utilizing an electron microprobe to map the precise chemical stoichiometry of thousands of individual indicator grains. The critical metric was the concentration of calcium versus chromium oxide within pyrope garnets. G10 garnets contain less than 4% calcium oxide and more than 4% chromium oxide, reflecting formation under extreme pressure in the presence of Harzburgitic mantle rock. Fipke knew that if a till sample contained these specific G10 garnets alongside high magnesium picroilmenites, the source pipe was almost guaranteed to sit within the diamond stability field. However, pinpointing the physical boundaries of a diatreme submerged under subarctic lake water required an entirely different analytical instrument, the airborne vertical magnetic gradiometer. In the Canadian Shield, host granites display relatively uniform magnetic susceptibility, registering a flat regional background signal. Kimberlites, by contrast, contain abundant magnetite and ilmenite minerals, giving them a distinct magnetic signature. Furthermore, because the kimberlite rock in diatremes had weathered into soft clays, it created subtle electromagnetic conductivity anomalies compared to the resistive solid granite surrounding it. In 1990, DIA Met Minerals contracted fixed-wing airborne magnetic and electromagnetic surveys flown at low altitudes over the Lac de Gras area. The flight lines, spaced just 200 meters apart, mapped precise total field magnetic anomalies. When geophysicists processed the data, circular magnetic lows and localized conductivity highs appeared as sharp, round depressions on the digital maps, matching the exact bathymetric footprints of small, isolated lakes. The definitive scientific confirmation arrived in the spring of 1992. Drilling through 2 meters of lake ice, crews recovered diamond drill core samples from the Point Lake pipe, and shortly after, the nearby Koala, Fox, Misery, and Panda pipes. Petrographic analysis of the drill core confirmed hypocrystalline kimberlite tuff and breccia containing fresh olivine macrocrysts. Laboratory processing of a 160-ton bulk sample taken from the Panda pipe yielded an average grade of over 1 carat per ton, with an exceptionally high proportion of gem-quality octahedrally shaped diamonds. What had previously been dismissed as an empty, glaciated expanse of Precambrian granite was suddenly reinterpreted as one of the world's premier diamond provinces. The discovery proved that sophisticated geochemical vectoring, combined with airborne geophysical profiling, could see through tens of meters of glacial till and lake water to reveal mantle structures that had eluded traditional geological mapping for generations. Yet, translating a remote scientific proof into an active industrial extraction operation in the Central Arctic presented engineering and environmental challenges on a scale Canada had never before attempted. The industrial transformation that followed altered both the physical geography of the Central Arctic and the economic structure of the Northwest Territories. To reach the kimberlite pipes beneath Lac de Gras, mining operators had to execute an unprecedented engineering feat, draining entire subarctic lakes and constructing massive water retention dikes directly across lake beds. At the Ekati Diamond Mine, which officially opened in October 1998, 5 major open pits, Panda, Koala, Misery, Fox, and Sable, were excavated deep into the granitic shield. At the neighboring Diavik Diamond Mine on Lac de Gras, constructed by Rio Tinto and Dominion Diamond, workers built 3.9 kilometers of rock-filled dikes through water up to 25 meters deep to isolate the kimberlite pipes from the surrounding lake before pumping out millions of cubic meters of water. The logistics required to construct and operate these remote complexes reshaped northern infrastructure. Because no permanent road exists to Lac de Gras, the mines depend entirely on the Tibet to Contwoito Winter Road. Built fresh every January over 400 kilometers of frozen lakes and tundra, this ice highway allows heavy transport trucks to haul tens of thousands of tons of fuel, ammonium nitrate, and heavy machinery during an 8-week winter window. Between 1998 and the peak production years of the mid-2010s, Canada surged to become the third largest producer of rough diamonds by value globally, extracting over 12 million carats annually, worth more than 1.5 billion Canadian dollars. Yet, this massive industrial footprint rests on fragile, continuous permafrost and sits directly within the migratory corridor of the Bathurst caribou herd. Environmental monitoring programs overseen by the Wequeji Land and Water Board, alongside local First Nations, including the Twincho government and the Yellowknife's Dene First Nation, track water quality, dust deposition, and wildlife movements around the mine footprints. The long-term environmental remediation liability for these sites is staggering. Reclamation plans require flooding the massive open pits to create artificial lakes that must safely reconnect with the surrounding natural drainage over decades, while processing waste must remain permanently frozen beneath engineered rock caps. As the mines reach the end of their operational lifespans in the 1920s and early 1930s, the region faces an impending economic shift. The closure of Ekati and Diavik will remove over 20% of the Northwest Territories' gross domestic product and eliminate hundreds of northern jobs. The physical traces of the initial discovery remain etched into the landscape. Deep circular pits hundreds of meters deep, framed by vast rock piles, sitting in a region where 30 years ago mapmakers saw only flat, featureless water. But as these industrial operations draw down, an even larger question remains about what still lies hidden beneath the thousands of undrilled lakes across the northern shield. The story of the Lac de Gras field does not end with the mines currently in operation. Geologists estimate that out of more than 300 kimberlite pipes identified across the Slave Craton, less than 15% have been thoroughly drill tested to significant depths. Exploration companies continue to conduct high-resolution airborne gravity gradiometry surveys over remote sectors of the Northwest Territories and Nunavut, searching for non-magnetic or deeply buried diatremes that previous magnetometer surveys missed entirely. What kept this vast diamond field unnoticed for so long was not a lack of physical evidence, but a rigid geological assumption, the firmly held belief that continental glaciation had ground away the surface mineral wealth, combined with a mapping system that treated lakes merely as obstacles to be drawn around, rather than active geological features hiding the bedrock beneath. For decades, mapmakers mapped the shores, and mining firms walked the granite, while the kimberlites sat untouched directly beneath the water. Significant questions remain unresolved. The precise mantle dynamics that triggered the simultaneous emplacement of dozens of kimberlite pipes across thousands of square kilometers 54 million years ago are still actively debated by volcanologists at Canadian universities. Furthermore, as regional permafrost warms, the geochemical stability of historical mine tailings and the hydrological balance of capped pit lakes present ongoing research challenges for the Northwest Territories Geological Survey and Environment and Climate Change Canada. The map of northern Canada appears complete, neatly rendered in topographic sheets and satellite imagery, yet the ground beneath it continues to rewrite its own history. Which place in your own province or territory has always struck you as geologically out of place? Or which part of this discovery surprised you most? Let me know in the comments below, and consider subscribing to keep exploring the hidden systems beneath the surface.